Okay, welcome to the types of machines notes review. It's just basically more commonly referred to as the simple machines review. There's a picture with multiple different ones. You can pause the video here if you want to identify them. I'm going to move on. Levers. Levers are the most complicated of most simple machines to figure out. Mainly because there's three different classes of them. And consists of a bar that moves or pivots at a fixed place, and this fixed place is called the fulcrum in the lever sense. The three things that change are the force, the fulcrum, and the load. They're all three of these are in every single class of lever, but the position of each is different. So let's identify. First class levers are very traditional seesaw kind of looking lever. Scissors are a good example of a first class lever. It's technically a compound machine because it's a wedge and a lever. Crowbars when you use to pull the nails out. A paddle in the canoe is a good example of first class lever. The fulcrum's in the middle. Load on the end. You put the force on this the other end over here, and closer you move this fulcrum to the load, the less force you'll have to put on it. Why? Because you got more distance there in between the fulcrum and the force. Second class lever, you have force on the end, load is in the middle, and the fulcrum's at the very end, the pivot point. Wheelbarrow is a good example. You have force on the handles, you have the load is in the bucket, and the fulcrum is the wheel. Yet another compound machine because it's also wheel and axle. Bottle opener is a good example. Crowbar is a good example of second class lever. Force goes here. Load goes on the metal part here, and then the fulcrum is the curved part. Third class lever is the most inefficient type of lever. It typically takes more force that you're exerting on something in the middle to do some work on the load. Perfect example of this is tweezers. Tweezers, you put the force here, the fulcrum's in the back, and the load or the work being done is up here at the point. Let's just go back to levers real quick. I generally find it easier to figure out levers by thinking about them in terms of examples. First class lever, I think scissors. I think wheelbarrow. I think seesaw. Sorry, I couldn't think of that. Second class lever, I always think of a wheelbarrow. That's just always the way I think about it. Force on the end, load goes in the bucket itself, right? So there's in the middle, and the fulcrum is the wheel. I just think this just makes so much sense. Force, load, fulcrum. Third class lever, I just think of tweezers. Tweezers are a good example. Salad tongs are another good example, right? You put the force in the middle of the salad tongs, the fulcrum is up here, and then the load or the work being done is down there at the end. So examples are the key to remembering levers. I'll leave these questions up for just a second. I'm not going to spend time to really go over these questions in the review video, but you can pause it and read over them, answer them if you want to. In fact, I encourage you to. Incline plane. It's basically a straight slanted surface. It doesn't have to be flat. It's oftentimes referred to as like a wheelchair ramp kind of thing, or like the ramps going into a back of a truck for a four-wheeler, but it does not have to be flat. It just has to be really a slanted surface. And stairs are always a really good example of an incline plane. They will basically generate a smaller force over a greater distance. For instance, you could pick up the scooter in here, but man, it'd take a lot of force to do that. But you wouldn't have very much distance to do it over. A ramp makes this allows the work to be done over a greater distance, which really just reduces the force. Anytime the distance increases, the force reduces. They are opposite to each other. But lots of good incline planes in your day-to-day life. Dump truck, stairs, wheelchair ramp. Wedge. Wedge is also an incline plane. It's technically a double incline plane that moves, right? You have two things that are slanting towards each other that make a point. Doesn't necessarily have to be a point like an axe, but an axe is a great example of a wedge. Chisel's a good example. The plow. This is a little wedge underneath the door. I would really think this is more of an incline plane, but it technically is a wedge used this way. Knives are wedges. Nails are wedges. Sharp point, it drives itself in between something, right? Saws are wedges. Screws. Screws are incline planes that are wrapped in a spiral. And you see the example down here in the bottom left. It doesn't have to be a screw in the sense that it is, basically the opposite to a nail. That's not necessarily what a screw is. A screw is any kind of thing that spirals around. You see an example here with the Archimedes hydraulic screw. The water is brought from this layer down here to up to here. It is definitely a screw. It's still an incline plane that goes around in a spiral. The spiral just, round. It goes around a fixed point. Screws are stronger. Will do more work on something than a nail will, because it applies a small force over a long distance. So every time it turns, it's incline planing. So which incline plane is a wedge, and it's basically a super nail if you think about it, because a nail is a wedge, which again is also an incline plane. Roller coasters often use screws. I mean, riding around in a circle is very, very fun, and this kind of thing does not have to be a thing you put in with a screwdriver. That's oftentimes a misconception. If you remember the OK Go video that I showed, the really cool music video, they had several like bowling balls going around a radius, which that in fact is a screw. Wheel and axle, very good one. Simple machine consisting of two circular objects of different sizes. The major confusion with wheel and axle and pulley, which we'll get to in a minute, is the pulley doesn't have the second circular object. It's really just one circular object. So there's no axle, it's just a wheel. So doorknob is a good example of wheel and axle, because it has the doorknob itself that you see in the bottom left. That is the wheel. It's connected to a small piece of metal on the inside that actually works the door mechanism, which is the axle. Steering wheel also connected to a small piece of metal on a piece of metal on the inside that connects to the other wheel and axle in your car, which is the front wheels. Screwdriver, another wheel and axle, right? This is a circular part. This is a circular part. The handle makes the work easier. Wheel and axle is one of those where you can really see work being done easier by a machine. You can still turn something with the metal part, but this part makes it easier. Doorknob's the same way. You can still turn that other little piece of metal inside of here, but it just makes it so much easier. Okay, onto the pulley. Like I was saying a minute ago, looks similar to a wheel and axle, but it's not necessarily a wheel and axle at all, because it's really a wheel. I mean, I'll give you that, but there's no axle, and that's what makes the wheel and axle different than the pulley. Simple machine consisting of a grooved wheel, holds a cable or a rope or some kind of thing. Two different types. You have fixed and movable. Fixed pulleys. They do not give you mechanical advantage, which means that it doesn't make work easier What it really does, it changes the direction of the work. You pull down, something goes up. A good example of this in your everyday life are mini blinds. You pull the string down for the mini blinds, and the mini blinds go up. It does not make the work easier. It just changes the direction. So it's, in that sense, I guess it makes it easier, but it doesn't make it force-wise easier. Flagpole is a good example of this one too. Raise the flag up that way. Just makes it more advantageous or easier to do on a daily basis, I guess. Movable pulleys do make work easier as far as the force required. It definitely is going to distribute it over more distance, which as a result of more distance, it means less force. So it's definitely mechanically advantageous, which means it just does more work with less force. You have the combination movable and fixed, which work in a system called a block and tackle. You see this a lot on sailboats. You also see it in places that have to lift heavy things like car engines or something like that. So has great mechanical advantage. Why again does it have great mechanical advantage? Because it increases the amount of distance that the machine does, right? Work is equal to force times distance, if you recall. And if you increase the distance, then the force decreases. So that's exactly why block and tackle works so well for heavy things. It increases the distance, thereby reducing the force, thereby making it easier for you to move something. You can pick up an entire engine out of a car with a block and tackle. Again, I'm not going to sit here and read over these. You can pause the video and look at them again if you want to. Compound machines. This is brief. Compound machines are two or more simple machines. Oftentimes things are compound machines. Scissors are a good example. Scissors are wedges and a first-class lever. Can opener is a compound machine. It's a wheel and axle. It's a third-class lever. It's a wedge because it cuts. It's a good example. Stapler, third-class lever, right? Fulcrum's here, right? Load goes here. I'm sorry, force goes here, and the load goes here. The work being done is here. It's definitely a third-class lever. But additionally, the second thing that makes it a compound machine is the staples. The staples are wedges, cuts through the paper. Here you see a block and tackle. Multiple pulleys, and by definition, if it's more than one pulley, it's more than one simple machine, therefore making it a compound machine. Pencil sharpener, a good one. Wheel and axle, wedges to cut it. Wedges are actually cut in an inclined plane or a screw. This is a pretty compound machine. It's a pretty ingenious invention that people just take for granted on a day-to-day basis. Bicycle's got a lot going on with it, mostly in the gears and wheels, right? Obviously a wheel and axle here, wheel and axle here. And the gears themselves are wheel and axles. Could technically be considered a pulley. I'll leave this up here in case you were questioning what some of these compound machines were. Machines become less efficient when compound machines because friction goes up. Remember, efficiency has to do with friction. Friction goes up with compound machines because there's multiple moving parts. And the more moving parts you have, they have more opposition to motion, which is friction. So you typically have to lubricate compound machines to make them work effectively to reduce the friction. I'll pause it here. Some of these are kind of a little bit difficult. This is really a high school presentation. Last thing I'll talk about is a Rube Goldberg machine briefly. If you saw the videos from Pee-wee's Breakfast Machine and the OK Go video and this kind of thing, you saw some good examples of Rube Goldberg's. Rube Goldberg is was a guy who drew cartoons of these complicated devices. And the only reason it's relevant is Rube Goldberg's are all full of tons and tons and tons of simple machines, levers and pulleys and wheel axles and everything. You can see them here, right? Wheel axle, lever. This is a lever when it hits down here. This is a wheel axle, right? So anyway, not going to harp on it. I just think in case it popped up on a question, you should be aware of what the significance of a Rube Goldberg machine is. And it's really just that it illustrates a lot of simple machines in a funny, kind of interesting, scientifically goofy way. So anyway, check out my videos on Edmodo and on YouTube if you want to check out a couple of Rube Goldberg machines for better explanation. And look for those simple machines. If you're going to watch the video, don't just watch the video and enjoy it. I want you to enjoy it, obviously, but look for the simple machines. Identify them. Call them out. It's okay. It's okay to learn and have fun at the same time. It technically is not illegal. Anyway, hope you enjoyed the video. Hope it helped review, study up, and so forth. And I'll see you in class.